Mr. Chairman, distinguished colleagues, ladies and gentlemen, good morning. My name is Dr. Aziz Arbai from l'École des Nouvelles Sciences d'Ingénierie ainsi in Tangier, Morocco. Today I'm honored to present mathematical paradigm shift in image processing. My talk is entitled Beyond Convolution, Theta 1, Image Reconstruction via Analytical 3x3 matrix function. Here is a brief outline of our journey today. First, we will identify the computational bottleneck hindering modern real-time image restoration. Then, we will introduce our paradigm shift, focusing heavily on the mathematical elegance of the Cayley-Hamilton theorem to bypass this bottleneck. Finally, we will look at practical application and review the experimental benchmarks on ARM architecture that prove our theoretical claims. Let's start with the context. We are in era of 4K and 8K video streams operating on low power edge computing devices like autonomous drones and nanosatellites. When we perform multi-channel color restoration or deep contrast enhancement, we traditionally rely on successive application of pointwise channel mixing matrices. The problem is straightforward. If you want deep transformation recurring in steps, the computational rates grow linearly. It is an theta n complexity. On standard embedded architectures, this linear dependency causes three major issues: unacceptable latency, massive energy consumption, and crucially, cumulative numerical drives due to IEEE 754 floating point precision limits. To solve this, we must move beyond the traditional layer-by-layer iterative approach. Our proposal shifts the operation entirely into the three-dimensional RGB color feature space. Is the mathematical representation of all possible color in a model based on the three primary channels, red, green, and blue. Instead of dealing with special neighborhood, we treat each pixel as an initial state vector x0 living in R cube. The iterative filtering process can now be modeled as discrete time linear dynamical system. The exact color state of the pixel at iteration n is strictly defined by xn equal a power n multiplied by x0. The practical challenge is to calculate n power of a. This brings us to the core of our problem. Since our transformation matrix A operates in R cube, its algebraic behavior is completely bounded by its characteristic polynomial P lambda. By applying the beautiful Cayley-Hamilton theorem, we know that every square matrix satisfies its own characteristic polynomial. Therefore, computing a power n doesn't require n matrix multiplication. Any n-step linear transformation can be reduced analytically to a simple closed-form second-degree polynomial. This is the major result. By evaluating the scalar an, bn, and cn, we collapse the iterative loop completely. The complexity drops from theta in to a strictly constant time theta 1. The challenge computational is now entirely mapped to finding these three scalars. Let's look at the most common spectral configuration when matrices are has three distinct real eigenvalues. By substituting this eigenvalue into our polynomial equation, we obtain a clean linear system defined by classic Vandermonde matrix. Since the eigenvalues are distinct, this matrix is not singular. By applying Cramer's rule, we derive exact, elegant, and explicit formula for A n, B n, and C n, as you can see at the bottom of the slide. The formula for A n as an example. The hardware just evaluated this direct formula, no loops, no iteration. Of course, real-world filters are not always so simple. Our framework mathematically resolves all spectral configuration. If two eigenvalues coincide, case 2, the Vandermonde matrix becomes singular. We solve this by taking the first derivative of spectral formulation. For triple eigenvalue, case 3, we use the second derivative. For complex conjugate eigenvalue, case 4, we map the equation to the real domain using Euler's identity, completely avoiding expensive complex floating point math in the hardware. Finally, to ensure the image doesn't saturate as n grows, we guarantee spectral stability at design time by bounding the spectral radius using the Gershgorin circle theorem. What does this mathematical purity allow us to do in practice? First, for iterative color space restoration, deep channel diffusion is computed instantly. Second, for multi-stage color filter synthesis, the depth parameter n becomes a continuous structural controller. We can emulate the behavior of extremely deep filter on strictly locked footprint without ever resizing the image or allocating new memory buffers. This slide highlights perhaps the most powerful hardware application of our method. In modern processing, we want adaptive filtering, smooth the flat area, but preserve the texture. Normally, this requires if-else branching logic, which completely breaks SIMD and ARM execution pipelines. With our analytical solution, the hardware always executes the exact same structure. AN A square plus BN A masse N E I. To adapt to local variance, we simply swap the scalar value AN BN C from a pre-computed micro-lookup table. The results zero pipeline styles and strictly deterministic processing speed. To prove this, we conducted rigorous benchmarks. We targeted resource-constrained system using a low-power ARM Cortex A153 processor. We processed standard HD and Ultra HD 4K video streams at 16 frames per second. The software was written in strict single-threaded C++ to isolate the poor algorithmic efficiency of our method against the standard iterative baseline. The numbers speak for themselves. Look at the standard iterative method for n equal 100 iteration. Processing a single HD frame takes over 415 milliseconds. Dropping the system to a sluggish 2 frames per second real time is impossible. At n equal 100, we achieve a massive 94 time speed up. We have empirically confirmed the θ1 complexity. But speed is useless if we destroy the image, because we evaluate the final state directly. We completely eliminate the cumulative truncation error inherent to the EAAA 754 floating point standard. The structural preservation is near perfect, with an SSIM of 0.9998 and no visual degradation. On the hardware side, because we eliminated the memory bottleneck of iterative loops, we observed an 85% decrease in physical power consumption on the ARM chip. This frees up the processors for other critical tasks. To conclude, by shifting deep transformation into the 3D color vector space and harnessing the Cayley-Hamilton theorem, we successfully collapsed n linear operation into one exact constant time polynomial. This makes 4K real-time processing viable on very low power edge hardware, while providing absolute mathematical transparency. Looking forward, we are already expanding this algebraic reduction to compress deep 1x1 linear bottleneck layers inside convolutional neural network, paving the way for exact lawless neutral compression. I have included our key references on the next slide for those interested in the foundational matrix mechanics or recent neural compression literature. Thank you all for your attention. It has been a pleasure, and I am now very happy to answer any questions you may have.